Okay, I'm going to prove that there are infinitely many prime numbers. Now, one thing to remember is that prime numbers are positive integers. 2, 3, 5, 7, 11, and so on. And we're going to do this by contradiction. Okay, so we're going to start the proof by saying suppose there are only finitely many primes. Now, if there's only finitely many primes, we can write them in a list. Say prime 1, prime 2, all the way up to prime n, where n is a natural number. So let's see. P1, that would be 2. P2, that would be 3, and so on to the last one, because we're supposing there's only finitely many. All right, there's not going to be enough room for me to finish this, right? So I'm going to have to wrap around and put it on the top. So I'll erase some stuff and put it up there. Okay, remember that we're proving there are infinitely many prime numbers. We're supposing for the sake of contradiction that there's only finitely many primes. And we decided we could, if there's only finitely many, we could write them out P1, P2 to Pn. Okay, so now let's consider the number Okay, so we're assuming there's only finitely many primes first, and we're going to derive a contradiction. And we're assuming that these finitely many primes are these primes here, P1 to Pn. So A equals P1 times P2 times Pn plus 1 is a natural number. Right? If all of these things are natural numbers, then when you multiply natural numbers, you get a natural number. When you add 1 to a natural number, you get a natural number. So A is a natural number. Also, notice that A can't be one of these numbers. Right? A is more than each of these numbers, right? It's each of these numbers multiplied together and then you add 1. So A is not one of those numbers. So A is not prime. Okay. Well, if A is not prime, then that means that one of our primes, P1 to Pn, must divide evenly into A. Right? Because like think about it, right? If you take a number, let's say 12, you can go like this, right? You have 4 and 3, 2 and 2. You can write 12 as 2 squared times 3, right? And you can do this for every natural number, every positive natural number. You can write it as its prime factorization. So if A is not prime, it's got to have a prime factor. It's got to have some prime number that divides evenly into it. So that means that one of our primes, P1 to Pn, must divide evenly into A. So one of our primes, let's say it's Pk, because I don't want to be too specific which one of my primes, P1 to Pn it is, Pk divides A. So that tells me that Pk times n equals A, where n is an integer. So P sub k times n equals A. So that means, now replacing this A, right, with P sub k times n, that gives you that P sub k times n equals P1 times P2 times Pn plus 1. But then we can divide both sides by P sub k. Okay, so P sub k is one of these primes, here. Now we don't know which one. We're trying to be totally general, but it divides into one of them, right? It is one of them, so it cancels with that one. So it cancels with P sub k here, right? Now what's the thing that came before P sub k? That's P sub k minus 1. What's the thing that came right after P sub k? That's P sub k plus 1. So n is equal to this product of primes, the product of all finitely many primes, because we're assuming there's finitely many primes, plus 1 over P sub k. Now here's the problem, right? Here's our contradiction. N is an integer. This number here is an integer. It's a product of primes. This is an integer. But this right here, 1 over a prime, this is not an integer. So we have an integer equal to something that's not an integer. And that's a contradiction. So it must be that our original supposition that there are finitely many primes is false. So therefore, there are infinitely many primes.